Good morning, it's me, Mr. Truman, back for another lesson in geometry. Today we'll be looking at similar triangles. Now we've already started the unit on similarity when we looked at something called dilations. And dilations are where we took a pre-image and we enlarged it or reduced it to make an image. Well, when we did that, we were creating what's called similar figures. And we denote that things are similar using this symbol right here, which you notice is just kind of a little squiggly line that we actually take from the congruent symbol. When we learned about congruent symbols at the beginning of this year, I told you guys that it had to do with same shape and same size. That's why it's a combination of not just being an equal sign, but an equal sign in that kind of squiggly line, if you will. All right, well, we're only looking at this symbol now, which means that we've lost the part about being the same size. We don't have that equal sign, and that's because similarity means same shape but different size. So we're going to be looking at some different ways today, 3 different ways in which we can identify triangles that are similar. And yes, I am always, as always, I'm fixated on triangles, and that's because if you've ever wondered what is it this class and always dealing with triangles, it's because all shapes are a combination of are always based on triangles. So once we prove triangles are congruent, it kind of takes us to all the other shapes as well. So the first way we're going to look at is called the angle-angle method. And the idea here is that if 2 triangles have 2 sets of congruent angles, then the triangles have to be similar. And that comes from the fact that triangles make 180. And so if they already have 2 sets in common, by default, the third one has to be the same, and therefore they have 3 identical angles. And again, we did not have an angle, angle, angle when we learned about congruence, and it comes from the fact that angle, angle, angle would never work for congruence because it doesn't imply that you're the same shape. It doesn't have to be the same, same size. It doesn't have to be the same size to have 3 angles match. And that's why we actually look at it in similarity. The next one is called the side, 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 which we do bring over from congruence. And side, side, side says that if we have 3 sets of proportional sides, not equal sides, proportional sides, and I'll explain that in a moment, then the triangles are congruent, or similar, not congruent, similar. And then the last one is called the side, angle, side. And that says if we got 2 sets that are proportional and the included angle, meaning the angle that holds those 2 sides together, the included angle is congruent, then they're going to be similar. So let's walk through 3 examples in which I will demonstrate each of these 3 different ways of showing similarity. So let's jump in with the first one. And I have 2 triangles, and I don't have any angles marked on them. I only have the lengths of the sides. And so what I want to show is that these 2 triangles are not the same size. I have eyes. I can tell they're not the same size, but I believe them to be the same shape. I'm therefore making them similar. Well, what I need to look for based on these 3 lengths is I'm going to look for something called proportional. So I'm going to compare one to the other. So if I start over here on the left, I'm going to look for, and I need some sort of system. I like to use small, medium, and large. And I'll start over here and say, all right, 6. 6 matches with 9. The 6 here and the 9 here, they are kind of matching sides. All right, well, let's look at the next one. The next up from that would be the 8 and the 12. And then the last one would be the 12 and the 18. All right, well, if you look at any of these are all matching. These are all equivalent fractions, and I'll show you why. If you were to reduce them like you were back in middle school and reducing fractions, you could look at this first one and say, wait a minute, 6 and 9, those both divide by 3. 6 divided by 9 is really 2/3, because 6 divided by 3 is 2, and 9 divided by 3 is 3. Look at this one, 8 and 12. Hey, these both divide by 4. 8 divides by 4 and gives me 2. 12 divides by 4 and gives me 3. Same thing goes here with 12 and 18. They both divide by 6. And guess what I get again? 2/3. Okay, so when I look at this, I'm not too concerned what this number is. I'm just concerned about the fact that it all matches. And that 2/3 is really the scale. This shape is 2/3 of the size of this one. That's our scale factor. But it all depends on how I'm comparing them. The same thing goes with if I were to do this, if I was to flip this upside down, maybe I started on the other side and I went like this. I said, all right, 18 divided by 12. And then I said 12 divided by 8 and 9 divided by 6. I could do this in reverse, and if I divide each of these, I could get the same thing. I would say I could get a calculator and I'd say 18 divided by 12 is 1.5, 12 divided by 8 is 1.5, and 9 divided by 6 is 1.5. It's not so much the number, it's the fact that I know that they are proportional and that I get the same number all 3 times. So without a doubt, when I look at these two items are similar. So I'm going to write a statement. And in a statement, I just want to simply give the one on the left a name, and I want to match it to the one on the right. So if I start over here and I say triangle A, B, C, I have to follow the pattern. I went from A to B, which was the medium side of the triangle. So over here I need to go X to Y, and then from Y to Z. So now I can write a statement, and then these two are similar, and then I say what rule did I use to determine them as similar, and I use the side, side, side. All right, so that's example number 1. Example number 2, we're going to look at a different rule, so we kind of can check this guy off. We've taken care of this one. And now looking at the second rule, let's see, second example here, what am I looking at? Are they congruent? Well, first off, I screwed up and I didn't give them a name, so I'm going to give them a name real quick. All right, so I look at these two and I want to find out if they are similar. Not congruent, like I said a moment ago, but similar. Well, I notice that they both have a 90-degree angle. So they don't have 2 angles, so I can't use that rule. And they don't have 3 sides. This side's blank, so I know I can't use the side, side, side. So what I'm looking at is called side, angle, side. I notice that I have 2 sides, and this is called the included angle. And over here I have 2 sides, and again, the included angle. So what I want to do is I want to write a proportion to make sure that these two are the same thing. So I'm going to take, and say I start with the 35. 35 is the shortest side of this triangle, and it would go with 7 over here, because it's the shortest side of that one. And then because I started on the left with this triangle, then I need to continue that pattern by sticking with that. Well, when I work these out, 35 divided by 7 is 5. And 120 divided by 24 is also 5. Another thing I can do, if I'm not good at, let's say I'm not that great at reducing my fractions. One thing that we could have done back here is we can also use cross multiplication. 6 times 12 is 72. 8 times 9 is 72. So we can cross multiply. If we're not that good at reducing fractions, cross multiply. Just like here, 35 times 24, 840. 7 times 120, 840. So that proportionally they're the same. Therefore, I know that these two triangles are similar. I keep saying that. It's going to take a while to break that. All right, so let's give them a name. So let's say I call this one on the left, I say CBA. I'm not going to call it ABC because then you're always going to think it has to be that way. C to B was the short side, so Z to Y would be the short side, and then X. And then I'd say, well, how are they similar? That's called side, angle, side. Oh, I think we put that little symbol there too. I forgot to do that on the other one. All right, our last example is a picture of 2 triangles. I've already done the side, side, side. I've already done the side, angle, side. So I'm gonna show you, this is called angle, angle. And you might look at this and go, how do I know that these are similar with such little information? Well, the rule here is that I need to have 2 sides in common. And when these 2 triangles intersect, this angle and this angle are automatically congruent by what's called vertical angles, way back in chapter 1. So with that, I can show that automatically these two have two angles in common. I don't know what this third angle is, just like I don't know this angle in the middle. I don't know what it is numerically, but I know that angle A and angle D have to be the same because triangles add to 180. They both got a 60, they both got this mystery number, so they both have to have that. So this is similar by, and I'm going to give it a name. So let's say I go with CBA. It's similar to, and I went from C to the 60 degrees. So I'm trying to find a reference to make sure I do the same on the other one. C to the 60, C to the 60. So I'll call this one over here CFD. And then they're similar by the angle similarity statement. All right, my last and final thing here is application. We use similar triangles all the time in things like surveying and architecture and mapping things out. For example, we're going to look at this one and it says, our principal is 6 feet tall and he cast a 27-inch shadow while standing next to our flagpole out there. So while he stands out there doing his little hall duty or passing duty, notice he's got a 27-inch shadow. The flagpole has an 11-foot 4-inch shadow. How tall is the flagpole? Believe it or not, I can figure it out. So let me draw. I may be married to an art teacher, but my art skills are terrible. But anyways, I don't know how tall the flagpole is, but I know that it has an 11-foot 4-inch. I don't like that number. I don't like working with two different things, so I'm going to turn everybody into inches. So 11 times 12 is 132, plus 4 more gives me 136 inches. I'm going to use inches. I don't like having two different ones. So I have a flagpole and I have a shadow right here. And then I've got our principal over here. Oh, this is going to be a great drawing here. It's like my best I got going. He's 6 feet tall, so 6 times 12, that's 72 inches. And he has a 27-inch shadow. Well, if I make these similar triangles, if I think of them as two similar triangles, I can figure out how tall the flagpole is. In fact, we might do that in class. So I'll start off. X for the flagpole should go with 72 for our principal. Since I went flagpole, then principal, flagpole, then principal. So using cross multiplication, I have 27x equals 72 times 136. 9792. I'm double checking that just because it's, yep. Now divide both sides by 27. Ooh. And I have 362. All right, so 362.7, so maybe we'll just round up, or maybe we'll just call it 363. All right, and now that's 363 inches. Well, if I divide that by 12, looks like it's about 30 feet. So 30 feet. So anyways, I'm working that out. I kind of worked out all the numbers to make sure everything was good. And yeah, it's about 30 feet. So I don't know, maybe down to the exact inch, but I'm pretty close. Better than crawling up there on shimmying my way up to the top of the pole. So anyways, I hope this helps. And that's it.